Okay, let's take a quick aside to think about nonlinear optimization. Okay, so the picture you need to have, like we drew last time, is I have some parameters alpha, maybe I have lots of them, the alpha 1, and I have some function I'm trying to minimize. Let's call it j of alpha to be consistent with what we were just using. Okay, there's a number of ways I can try to numerically find the minima, let's say, or a local minima of some function like this, right? Most of them involve starting with some initial guess, evaluating the function at that guess, and then somehow locally estimating the curvature or the smooth or the gradient of the function here. Okay? So if I do exactly what I cartooned last time, I evaluate my function at a point, I calculate the gradient of that point, which would be a function like this, and then move down the gradient. So if I do something like my alpha at n plus 1 is my alpha at n. Let's call this alpha at time step n. Let's call it time step n instead of, to be distinct from parameter n. On the nth step of my algorithm, I'll update my guess at my favorite parameter alpha by looking at evaluating the function and moving down the gradient, right? And I'm going to do that with some rate, some scaling. So call it a learning, people call these learning rates, for instance. And that will work, and that will find some path that will get me down to the bottom here, because when I get to the bottom, the gradient will equal 0, my update will stop, and this thing will converge to a local optima. The problem is I hate having to pick this learning rate, and it can take a long time to get down to the optima, especially if the magnitude of the gradient is very different in different directions. This is called a first order method. Or gradient descent. And although it's back in fashion for extremely high dimensional parallel optimization, we almost never do it in our trajectory optimizations. Okay, you can imagine, having called this the first order method, that there's maybe another solution out there, which would be the second order methods, right? Which would be the Newton methods. And the idea with the Newton methods would be that I'm going to use this, I'm going to evaluate the gradient, but I'm going to make a locally quadratic approximation of my cost function. Okay, you can do that by evaluating only the first order gradient and making a guess at the quadratic term, or you can evaluate the first and second derivative at my point. Okay, but I'm going to make a locally quadratic approximation of my objective function, and then instead of going slowly down the gradient here, I'm going to take in a single step, I'm going to jump straight to the optima of my local quadratic approximation, since I know how to find the minimum of a quadratic function. That'll give me a new value here. I'll make a new quadratic approximation, which should be more accurate evaluation of the approximation of the function close to the origin, and I'll jump to the origin. And these second order quadratic methods can converge much faster. Okay. They also have a very natural way to handle if there's constraints, right? If I have constraints in my system, they handle constraints naturally by making, so I get a quadratic approximation. I make a local quadratic approximation of my objective, my cost function, my objective function, and a locally linear approximation of constraints. And then one way to do it, for instance, is if I make these approximations, is I can solve a quadratic program. To jump to a new to the approximated local minima. Then I'll evaluate my function at that point, make a new quadratic and linear approximation, and continue. Wash, rinse, and repeat until you find a solution. This is called a sequential quadratic programming method. It's just one of the second order methods that you can apply, but it's one that we use frequently in our work because it works very well for these problems. In particular, some of the parameterizations we're going to write down are sparse in important ways, and there's nice ways to take advantage of the sparsity of the parameterization in these SQP methods. One numerical package that does this for us that we use a lot is called SNOPT. It's a solver written by Philip Gill, which is called Sparse Nonlinear Optimization, which is a sparse SQP method. And it's packaged with Drake. Thank you to Phil. Now, it used to be, interestingly, when I started, I realized, when I was a young, ambitious programmer, I used to think, oh, there's nothing hard about any of these methods. I know how to implement them. I'm going to implement them all myself, right? I can implement gradient descent for sure. I can implement Newton methods. There's nothing tricky about any of these. But I've learned the error of my ways. Okay, so it turns out the package SNOPT. It's an SQP method, the basic SQP method. There's nothing hard about it. But somehow these solvers, the good, robust solvers, have lots and lots of little numerical tricks, secret parameters, things that will work with poorly conditioned inputs, bells and whistles that are very hard to replicate in your own code. So for me, I've given up trying to compete with the solvers and will happily download and use a commercial solver to solve my nonlinear optimization problem today. So actually what you'll see if you look in Drake, there's a class hierarchy where you can formulate a nonlinear program. I can show you. You can formulate a nonlinear program. You can add constraints of different types, add your cost function, and then you can basically you can set a different solver type and call solve. And this abstracts away the details of the numerical implementation from the problem formulation, but it lets us use a variety of commercial solvers to solve the optimization problems that we carve up.